Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So let's begin with a description of MANETs. MANETs are mobile ad hoc networks. They're basically wireless networks in which the wireless hosts act as forwarding routers as well as end systems. So a key component of MANETs is that there is no routing infrastructure. There's no access point, there's no base station, etc. So the nodes themselves have to do the routing. A key characteristic of such networks is that the network topology changes frequently and unpredictably. However, we are still interested in such networks because they have one very important key benefit. They are easily deployable communication systems in infrastructureless scenarios. So because of this key benefit, MANETs have many important applications. For example, they can be used for military battlefield communication and also for reach-back networking from the people in the field. They can provide mobile multi-hop access to infrastructure such as mesh routers, WiMAX node access points. They can be also very useful in emergency services. For example, after a disaster, search and rescue operators can use this without relying on an existing infrastructure which might have collapsed or failed. Finally, there are many collaborative distributed applications. For example, peer-to-peer file sharing, voting technologies, gaming, etc., which sort of takes these groups of users and opportunistically networks them to create many applications. So a key thing to see here is that the application performance in these MANET networks depends on the efficiency of the routing techniques used. So typically you can think that most applications would require some kind of unicast primitive. So any one node would like to communicate with some other node. This is used by many applications. Oftentimes multicast communication can also be useful for many different applications. For example, if you want to send a currently received satellite photo to various soldiers, you need some kind of a multicast primitive. An important requirement to maintain application performance is that the routing should scale with network parameters. These parameters could be the number of nodes in the network, number of traffic sources, etc. So the challenge is, this is not very easy to achieve. So the challenge is how do you provide these primitives, these unicast and multicast primitives, given that the network topology is changing frequently and unpredictably. So as you can see, MANETs are mobility intensive networks. So they're very different from the wireless mesh sort of community networks. They're mobility intensive networks, and the challenge is how do you provide efficient and scalable routing in the face of this mobility. So since there are these two primitives I talked about that are useful for almost all the applications in MANETs, I'll first begin with one of them, unicast routing. So to give you a context, the historical context for this field, you can see that in the early 90s, we really had the availability of off-the-shelf wireless network cards and laptops. So that basically began the interest in this field to sort of opportunistically form networks. In '94, we had the first papers on DSDV and DSR routing, and these sparked tremendous interest in MANETs, both in the research and academic communities. In '98, we had a very well-cited paper by Brock et al. From CMU, which compared the leading MANET routing protocols. So all these protocols which were being compared have one common disadvantage. So they are all topology-based protocols that rely on discovering and maintaining global state. So what I mean by this is, for example, let's assume that everybody here is a network. I want to find a route to a destination, so I just flood the network with a broadcast message to discover a route. But 2 minutes later the person might move away, and the nodes in between might also move away. So I need to continuously flood to discover this global state. So this sort of a flooding-based approach does not scale. The discovery and maintenance of global state does not scale. So what do we do to have efficient routing in large-scale MANETs with this mobility happening? So fortunately, around 2000, there was this new proposal called geographic routing, and that's the GFG and GPSR. So the main idea here is you assume that each node knows its geographic location. So for example, you could imagine that this can happen outdoors by using GPS, or you could in indoors you could use many localization systems proposed by, say, Cricket, or there are lots of these systems available. So you assume that each node knows its geographic location, and then routing can be done by geographic forwarding. So how does geographic forwarding work? For example, if A wants to send a packet to G, what A does is in every packet going to G, he inserts G's location in the header of the packet. So how would C forward such a packet? So when C sees this packet from A destined to G, he knows his neighbors. So he's doing periodic one-hop beaconing. He knows his location. He knows the location of his neighbors. So all he needs to do is he needs to find the neighbor that is closest to the destination from among all his neighbors and just forward the packet to that neighbor. And this is done so on in the same manner until the destination is reached. So this basically is routing using local state. So each node just needs to know its neighbors, and with that he can route the packet to the destination. So this relies on local state, and hence there is no end-to-end route discovery. So there is no flooding trying to find where the node is. So because of the fact that there is no end-to-end route discovery, geographic routing scales well. However, there is a missing piece of the puzzle here. We made a very big assumption saying that, okay, A knows G's location, so now I can route a packet with local state. But the problem is, where is the destination? So a geographic routing protocol needs a location service. So the emphasis has shifted, the challenge has shifted from that of finding a route in a scalable manner to that of providing a location service. So the main thing is, in order to enable this scalable geographic routing, you need a scalable way to find the location of any node in the network. So essentially, to provide scalable unicast, you need a scalable location service. And so the challenge is shifted to finding such a location service. And the main important thing is the location service should also be scalable to ensure that the unicast routing or geographic routing remains scalable. Because even if you route using local state, but your location service is flooding the network, it's of no use. Because you come back to the original problem again. So the main thing to see is that location service determines the scalability of unicast protocols in MANETs. So now I'll talk about our proposal, that's mobile geographic hashing. I'll show you how this can be. Sorry.
Before you continue, location you really want to use in a loose sense. I have no idea what latitude and longitude I'm at now. I know I'm in building 113, right? And in a mobile network, maybe I just know I'm near that transmitter because I can hear it, right? And I have no idea otherwise. And you have to turn that into a location, or at least it may be useful.
Right, so there are many systems that actually use this kind of profiling. So suppose you're in this building, you can use access points nearby to sort of pinpoint your location. So there are many existing systems that can work and provide you this position indoors. So you're right, that's very important. You need a different kind of location service at any point in terms of your own location. But after that, what we need is we need a way of telling every other node what your location is, and that needs to be scalable. So what mobile geographic hashing does is, so assume that this is a two-dimensional space xy. So assume that this is node A and he wants to store some data in this network. So what A does is simply hashes this data to a location. So hash of this data is some xy location in this plane. Okay. Once this hash is done, what you can do is you can simply use geographic routing to route this packet towards this location. So you can take any message and route it towards this location. And since this location is purely a hash, a random function, there may be no node at this location, but there will be some node closest to this location. So this message is then stored at a node that is closest to this location, and this node is known as a rendezvous point for the storage of this data. So what happens with mobility? So when you have mobility, some node may come closer to xy than B. But remember that for geographic routing, nodes are continuously beaconing their one-hop neighbors, so they know each other's locations. So when this happens, we can easily perform a handoff to make sure that this remains consistent. So notice that this is quite neat. So what we have done is we have decoupled the location of data from its storage. So every node can locate a data at some point, and every other node knows where this data is located. So if anybody else wants to find this data, he can also hash, and he knows it will be stored here. However, nobody knows which node it is going to be stored on. And that can be affected by mobility, and that is changed continuously as mobility happens through a local handoff process. So let's see how we can use this. Are there any questions about this? Okay, so let's see how we can, yep.
So B has it, what if B just moves away from X and Y? Is it clear who's the next?
So you're saying if there is a sparse network, so what will happen is there's nothing around this point. So there'll be some node here who will find that he cannot find a node closer to the location than himself. So what you can do here, you can do a planar graph traversal. So you can use a right-hand rule to traverse this graph around the hole and converge on the node that is the closest to the location. This is mathematically proven to be true. So even if there's nothing here, there's some. So suppose you stop at this point, you can start traversing here until you find the node which is closest to this location. And this is called perimeter forwarding. This is a well-known technique. So you route around the face of a planar graph so that you can find the node closest to this location. And this problem, like you say, will occur in sparse networks, definitely. So let's see how we can use this to build a location service. So let's assume A wants to store his location in the network so that other people can look it up before it routes a packet. So what does A do? A can simply take his own IP address or his MAC address, whichever he wants, some unique identifier, and hash it to a location. Subsequently, A can send an update packet to that location. So the update packet contains his current location, that's his XY coordinate, and it contains this hash location. So that packet is routed to this node B, and so B becomes a location server for A's location. So B is basically storing A's location. So now if somebody wants to find, suppose D wants to send a packet to A, all he needs to do is just hash the A's ID, find the location here, this will automatically be routed to B, and B is going to reply to A with the current location of A. B will reply to D with the current location of A. Once this is done, D can just route a packet from here to here using geographic routing. Notice that there is no flooding anywhere in this network. Both these packets are unicast, and the reply is also unicast. So there is no flooding here, so this approach is very scalable. Finally, when you have mobility, some other node may come closer to the data location point, and so this guy will do a handoff to him. He'll become the new location server for A. And since he is a new location server, any other query in the future will automatically be routed to him. And not only D, anywhere in the network, if they want to know the location of A, they can just do this hash, come here and get the location. And the main idea is because we have decoupled the data location from which node is storing the data. If you had to actually say that A's location is stored in B, we'll have to follow B around. And this is a chicken and egg problem. So then we need B's location. To know B's location, we have to find his location server. So this goes on and on. So this is the only way we can decouple these two problems, which occur due to mobility. So now, after showing you how mobile geographic hashing helps you build a location service, I now have to convince you that this location service is actually scalable compared to what's out there already. So I'll do this through analysis and simulation results. So there are a variety of location services that has already been proposed for finding the location of a node. And at the highest level, they can be classified into flooding-based and rendezvous-based. So flooding-based, as you can think, is very simple. Everybody just floods their location all over the place, so everybody knows everybody's locations. And this obviously is not scalable because it costs a lot of energy and transmissions. In rendezvous-based, the source and destination node decide in a distributed manner upon a common rendezvous point to exchange the location. So in this, the nature of the rendezvous actually differentiates it further. You can have a quorum-based rendezvous location service in which you decide a subset of nodes which are going to store a location. You can have hashing based, so GHLS, which I talked about, is a hashing based. The service I just talked about is GHLS. So you can have a hashing based service, or you can have a hierarchical hashing based service, is GLS. So the main thing is these flooding based location services are not scalable. So there's no point comparing to them at all. We'll concentrate on comparing our location service built using MGH with these other two location services that are well known and scalable as well. And we'll show why it's better. So let's look at the first location service. This is GHLS. So as the name suggests, it has something to do with the X coordinate and the Y coordinate. So if there's a node A and he wants to update his location, so he takes his own location XY and he broadcasts it in a north-south direction. So he broadcasts it to his neighbor. Sorry, he unicasts it to his neighbor, and the neighbor sends it to another neighbor such that it remains close to the north-south axis. So the update travels in this direction. So now if a node just wants to know the location of A, all he needs to do is to do a query in the east-west direction. And it's bound to converge at some point. So even with mobility, you can guess that since this is a unicast, and so these updates are both unicast and broadcast. So it will not be just one thin node, which could, if there's only one node, it could just break apart with mobility. So there are multiple nodes in this column that have the location of A. So if D can just hit any one of them, he's going to get the reply. And again, there's no real flooding in the whole network. There's just flooding along one column and one column here. So that's why it's better than doing flooding. So reply just comes like this. So this is XYLS. The next service is GLS. So this is much more complicated. This was in Mobicom 2000. So the features of GLS are hierarchical decomposition. So they break up an area into different grids to have scalability. I'll show you how that's done. They also do namespace hashing. So they do something like a DHT in the internet. They put the location on a node whose ID is the least greater than anybody else in that square. So if I am 2, my location will be stored on a node 4 if there's no node with ID 3, something like that. I'll show you how that is done further in the next slide. Another important thing about GLS is that the location is stored at multiple servers. So remember in GHLS we are just hashing and putting it on one node B. This location service will actually do it on multiple nodes. So the idea here is that each node N is going to store its location on all these location servers, multiple location servers. So N is the node who wants to store its location, and S are the location servers, all the S's. You had a question? Yeah. So all the S's are N's successor in each square. So the terrain is divided into these quad tree-like structure. So for example, this is order 1 square. Those 3 are order 1 squares. These are order 2 squares. And these are order 3 squares for N. So in each of these squares, N will choose a node who's the guy with the least ID greater than N. So suppose in this square, suppose N's ID is 1. And this square we have nodes 3, 4, 5. We'll choose 3. Something like that. I'll show you a better example how this is done. So let's assume this is a network and it's been divided, and 2 wants to store its location in the network. So what will 2 do? So 2 wants to store its location in each sibling square. So he stores the location here on one node, here on one node, here on one node, in this square on one node, in this square on one node, and this square on one node. So he needs to send an update to each of these locations. So first of all, he'll send it in the direction of this square. And the first node that gets it will check, okay, is my ID the least greater than 2? No, because he knows about 9 already. And the reason he knows about 9 is because he's a location server for 9. So when 9 stored its own location, he would have stored on 11. So there is this sort of interplay between in this scheme. So once this happens, 11 knows about 9, so 11 is going to send it to 9, and 9 will become the location server for 2 in this square. Similarly, when the update goes to this square, that's the only node, so he's the node with the least ID greater than 2, so he becomes the location server. And when you go to this square, 23 will know that 6 is closer to 2, so it goes to 6, and it's stored there. So again, the reason that 23 knows about 6 is because 6 used 23 as a location server. So now how do you do so if you want to do a larger square on the other side, so you'll do in a similar manner. So one will just send a message towards that square. You can just say, I want to go to that square. The first node that gets it will again check. So he knows about 9 again. 9 is closer to 1. He's going to go to 9. 9 knows about 2. So he's going to go to 2. And 2 will become the location server in this larger square for 1. So as you go further and further from yourself, you use lesser and lesser location servers. So now how do you query for a location of somebody else? So suppose node 23 wants to query for 2. So what will he do? He'll first look at his own table and he'll see that 6 is closer to 2. He'll first look in his own square. He'll go to 6, and 6 will already have 2. And 2 is the closest, so 2 becomes a location server. So in this manner you can find so they don't even know who the location servers are. So you can query for the location server without knowing where they are, and you can update your location server without knowing who they are. So this is GLS. An important thing about GLS is the query is locality preserving. So if you notice, if the source and destinations are in the same square, the query is always limited to that square. So this is different from GHLS. So in GHLS you could have a problem. If the source and destination are here, you could have to query here and go back like this. So this is a good thing about GLS. So we'll evaluate how this plays in practice. So what we did is we analyzed these 3 location services, and we found expressions that show you the update transmissions, the average query path length, and the average query response path lengths. So the query and the query responses only differ by some constant factors, so it's not very interesting. What is interesting is that if you look at the updates, both XYLS and GHLS, what we are proposing, are sort of exponential with the hierarchy height. So hierarchy height is the size of the network. So if you see GHLS and XYLS grow as order of 2 raised to h, whereas GLS with this nice quad tree structure grows as order of h. so it's linear. So obviously GLS should be asymptotically scalable. However, guess what? If you actually plug in these equations and you try to plot till when GLS is more scalable, you'll find that only after a network size of 25,000 nodes do you really need GLS to achieve scalability. And this is because of the constant. So there's a large constant hiding in the O notation. And if you look at MANETs, it's not clear whether we can construct MANETs of this size yet. Most of the MANETs probably will think of 500 to 1,000 nodes. So for practical scenarios, we argue that GLS is, although it's asymptotically scalable, for practical scenarios it doesn't matter because the constant is larger.
How do you get this graph? Do you just plug in the equation?
Yeah, we plug in the equation and we assume a density for our particular hierarchy based on what they did in their paper. So this is an interesting thing. So in MANETs, you don't have an unlimited size problem. You don't have a problem of unlimited size. So the asymptotic scalability is not very important unless it's going to affect you even at a small network size. So apart from the analysis, the analysis doesn't tell you what happens with mobility. So we also want to compare them using simulations. So we use the GlomoSim simulator. This is a well-known simulator used for wireless networks. It simulates the IP layer, the MAC layer, wireless transmission, fading, etc. So we use geographic forwarding. We assume 11 Mbps radio, 250 meters range. The mobility ranges from 1 to 9 meters per second, randomly chosen. A pause time is 0 seconds. So pause time basically means a node moves to a location, pauses for a certain time, then moves to a different location. So pause time of 0 seconds means he doesn't pause at all. So it's very high mobility. Then in the traffic, every node initiates 15 queries to randomly chosen destinations between 30 and 300 seconds. This is the same as in the GLS paper, so we can compare to them effectively. So the idea is every node is going to do 15 queries for locations. And we're going to see how it performs. What we're interested in is what is the delivery ratio, what is the success rate of the query, what is the overhead. So these are the two important things because the overhead decides the scalability and the success ratio tells you how good your service performs during mobility. So the first thing we see is we use a static scenario, no nodes are moving. This is the same as analysis. So there are 600 nodes in a 2500 meter by 2500 meter area. So the first thing we can see is that GHLS has the lowest protocol overhead compared to the other two services. Secondly, GLS has higher updates than GHLS. Because of this complex hierarchy which it has to travel, it can take more and more transmissions to actually select the location servers. Finally, query transmissions is also highest in GLS since it reaches a destination who then finally replies with its own location. So GLS queries travel up the hierarchy until they reach the actual destination who then replies with its current location. So the main thing from this slide is that the results match the analytical predictions very well and GHLS outperforms GLS and XYLS. So now let's take this, sorry.
So what was the quantity that grew exponentially versus linear?
That was updates. That was the number of updates.
Updates.
Right.
But you say GLS has higher updates, and that's for the size of the network?
Right. That's for this size. This is a smaller size network for 600 nodes. So in that graph, only after 25,000 nodes will the updates be less than GHLS. So actually for these network sizes which are typically considered, it has higher number of updates.
What's an update relative to protocol overhead?
Okay. So an update is basically you take your location and you insert it somewhere. So when I'm moving around, I have to keep updating my location every d meters, say. So when I'm here, I'll update it once, and maybe after 5 seconds, I'll update it again. So that's an update. So the updates are proactive. They have to be done continuously based on your mobility. So that's why they are the main factor in the overhead.
So what does it have to do with the location service, your update rate?
Because the way you do the updates, the location service determines the way you do the updates. So the updates in GLS have to travel up this hierarchy to select the location servers. So the number of times you do it, it's going to increase your overhead. Because updates are part of your overhead of the location service. So the location service has 3 overheads. One is how do you update your location, how do you query your location, how do you get the reply. So these 3 things are part of the overhead in the location service.
But if I am going to issue an updates at a certain rate depending on my speed of motion, right? So that doesn't have to do with which location service.
So you're right. The updates sent are not, it's not about the updates sent, it's about the update transmissions, like how many hops does it take, how many transmissions does it take to choose a location server. So it's like you're right in saying that the updates emanated from the node will be the same. That's true. But it's more about how are these updates finally stored at the location server. And that's where the location services performance comes in.
Okay, and what is protocol overhead?
So protocol overhead is basically any messages you need to compare the, protocol overhead is just the sum of the update query and query replies. Because all these are part of the location services. So it's just total overhead. So let's see what happens when you take the static network and make it mobile. So we took the same scenario and just made it mobile. So what happens is, the first thing that you see is that GLS updates increase by 82% because of boundary crossings. So in GLS, if you remember, there is this quad tree structure. So the moment you leave a boundary, your square has changed. So now you have to select new location servers because all the ID mappings, everything have changed. So your GLS, the updates increase by 82% due to boundary crossings. At the same time, for GLS and XYLS, updates actually decrease. The transmissions actually decrease. And the reason is that when you're mobile, so when you're static, you have to keep sending an update at 40 seconds. So when a node is static, it just chooses a period and sends periodically. Whereas mobile, he may or may not be moving fast enough to send updates. So that's the reason you have a small gap. Finally, the transmissions for query for GLS increases by 12%. That means GLS query is affected by mobility. So the final conclusion is that GLS is more susceptible to mobility, and the gap between GLS and GHLS is doubled. So it's not only the fact that it's less, you don't care about asymptotic complex scalability, it's also the fact that in mobility, a complex location service like GLS performs badly. So one thing people could say is that we are not being fair. So I talked about the locality preserving query in GLS. So if your source and destination are close by, you will not traverse very far away. So we wanted to compare the effect of locality in the pattern. So what we did was, we have increasing levels of locality. So locality basically means that, suppose you have X out of Y, it means that 10 out of the 15 queries go for nodes who are close to you. So for example, both the source and destination are less than 750 meters away from each other. So in this case, GLS should work very well because it's optimized for this kind of a scenario. So when we did this, as expected, the query overhead reduces with increasing locality for GLS because the traffic pattern is more and more local, so he doesn't go out of his square. So the query overhead is reducing. However, at the same time, the query overhead for GHLS also reduces because nearby nodes look up similar destinations. This is just like web caching, where you have locality among clients. So if they both look up similar, so if one node looks up a location and another node wants to look it up, they can just use a cache it because each node along the way is also going to cache the location updates. So because of caching, GHLS also benefits from locality in the traffic pattern. So the point here is that you don't need a complex hierarchy and to really exploit this locality in traffic pattern. You can use a simple caching along the path to exploit this locality. Finally, we compared these three location services to previously known unicast routing protocols, AODV and DSR. So AODV is from Nokia and UCSB, and DSR is from CMU and Rice. So these protocols don't use geographic routing, whereas all these protocols use geographic routing. So you want to compare how these protocols compare to each other when used in a large network. So the first thing we see is that we're going to scale the network from 0 to 2000 nodes. The y-axis is the packet delivery rate. How many packets are delivered depending on how many are sent. So it's the ratio of packets delivered upon those sent. So first let's compare the three location services. As you can see, GHLS has the highest packet delivery ratio, very close to 100%. XYLS has comparable packet delivery ratio, however it comes down slightly compared to GHLS. You can see that GLS deteriorates rapidly as the network size increases. So the GLS paper actually used a network size of 600 nodes. So at this point they perform pretty well, but once the network becomes larger and larger, this complex hierarchy is difficult to maintain in the presence of mobility. So the packet delivery ratios fall to around 80%, so 20% of the packets are lost. And this is because the locations are stale or because you just could not get a query reply. Finally, if you look at the other protocol, AODV and DSR, so DSR is really horrible. It basically cannot deliver 60% of the packets once the network grows to 500 nodes. The reason is you're doing this flooding, which is increasing the overhead. Another thing is DSR includes the whole route in the packet, so source routes. So when you discover a route from A to G, so it'll put A, B, C, D, E, F, G in the packet itself. So this grows with the network size, and that makes it unreliable. So the packet delivery ratio drops rapidly. We also use the AODV protocol with a lot of scalability extensions. So that performed pretty well, but even then the packet delivery ratio drops down as you reach larger and larger network sizes. At the same time, if you look at overhead, you can see that both the topology-based protocols, their overhead increases very, very fast as network size increases because of this flooding-based approach, which does not scale. And if you look at GHLS, you can see it's a very nice flat line, increasing slightly as the network size increases. And the reason for this is it's only using unicast. So the only thing that's going to change is, okay, my hash will be slightly further from me. That's the only thing that changes in GHLS. Everybody else has to deal with this complexity and flooding and all those other things. Okay. So in summary, we found that our location service built using mobile geographic hashing outperforms GLS and XYLS for practical network scenarios. So if you consider a practical network scenario in which the nodes will not be very high, it performs very well. We find that GLS, which was previously known to be the most scalable location service, is highly susceptible to mobility. Finally, we also find that locality in traffic patterns can be exploited by simple caching rather than using this complex hierarchy in GLS. And the last conclusion is that non-location based protocols with scalability improvements work well only up to a few hundred nodes, maybe like 100, 200 nodes. So you want larger networks than that, you have to use geographic routing. So the take-home messages from this part of the talk is that the location service critically affects the scalability of geographic routing, and location service is key to the scalability of unicast routing in general. We showed how mobile geographic hashing is an effective technique to build location services in order to scale unicast protocols. Two other interesting findings from this study is that when you talk about asymptotic scalability, the constants really matter, because we're not dealing with a computational problem here, we're dealing with a real network. So it matters in terms of what kind of network you're looking at. So the quantitative model shows that GHLS outperforms GLS for small practical networks less than 25,000 nodes. And even if you assume that we can do this, let's assume we can have 30,000 nodes in a network, even then asymptotic scalability is not enough. The reason GLS got asymptotic scalability is because it's very complex. It's doing this hierarchy, hashing, quadry, etc. This complexity reduces resilience to mobility. So in such networks, complexity is a problem. It always causes problems when mobility is there, because there can be lots of inconsistencies in routing. So simplicity in GHLS also provides it robustness to mobility. So two other take-home points from this from this talk is that MANETs really require simple, robust protocols rather than complex protocols which may be asymptotically scalable. So are there any questions at this point? So I'll move on to how we can use MGH to provide scalable multicast. Thanks. So multicast is another important primitive that we require in MANETs. So again, this field has developed in this manner. In the early 90s, you had these off-the-shelf network cards and laptops, so people are interested in this opportunistic networking. In 94, as I said earlier, we had the first papers on unicast routing. So in 98, we had the first papers on shared tree multicast. So you can have a multicast in a mobile network and you share one tree among them, so you don't build multiple trees. Then in 99, there was the first paper on mesh-based multicast. So what they want to say is in a tree, in a mobile network, a tree can break very, very easily. It's very fragile. If one upper internal node moves away, the tree breaks. So they propose a mesh-based approach in which you have multiple opportunities to receive packets. Finally, in 2000, there was a comparison of these multicast proposals in Infocom. However, similar to the unicast problems, there's again a problem here. So topology-based protocols, they rely on discovering and maintaining global multicast session state. And this does not scale. For example, you need to know who are the group members. You need to know where they are right now, or in terms of you have to make a tree so that you can reach them. So the mobility and dynamic group membership causes overhead, and this overhead increases with the number of groups and the size of the groups. So the current topology-based protocols, again, are not scalable. So can geographic routing come to our rescue again in this place? So for example, you can think of the fact that, okay, like there's a 100 node network and there are 20 group members. So what if I knew who these 20 group members are, and I know their locations? If each node is provided this information, he can simply construct a multicast tree on his own. So you can use, so this is like a Steiner tree problem or a minimum spanning tree problem. You can just use the locations and build a graph based on the geographic distances between the nodes. So again, this requires a location service. So the problem is, how do you obtain the group members in their locations? And this problem is different from unicast, because it's not like you're trying to look up the location of a destination node. You want the location of all these group members, and you want to know who the group members are. So this is a bigger problem than the unicast problem. Another problem is, since the source is constructing the tree using the group members and their locations, there is some encoding overhead. So when I want to send a multicast, I'm just going to say, there are two ways of doing it. I'm just going to say, okay, A, B, C, D, E are the group members, and I'm going to put that in the multicast packet. So when it gets to A, he can see A, B, C, D, he can compute the tree again and decide how to split the tree. He can say, okay, for B I have to send a unicast, for C, D, E I can just send it down one branch. So you can do it this way. Or you can build a tree and use the preferred sequence of the tree to sort of encode the tree in the packet itself. So there is some encoding overhead to be dealt with when you use this geographic routing based multicast. Another important thing about multicast is that it's different from unicast. Not only do you need scalability with the number of nodes in the network, you need scalability with the group size. You need scalability with the number of groups, and you need scalability with the number of sources. These two problems are not there in unicast. So now I'll show how we can use MGH, which I use for unicast, to also build a scalable multicast protocol that displays all those properties. So a very simple thing to do is, a first cut approach is what? You just take MGH and use a group name. For example, this is a search and rescue operation, and there are these medics among other soldiers and fire personnel. So all the medics want to form one group. So I'm just going to hash medics to a location just like before, and this message will be routed to a node B, which becomes a rendezvous point for this multicast. So for example, if I want to join the group medics, I will hash medics and send a join message to this node, to this location. If I want to leave the group medics, I can do the same thing. If I want to update my location, I am a part of medics and I want to keep updating my location so people can find me, I can just update using this technique. But there's a problem here. This is not, and again as we know, the mobility can be handled using localized handoff. So if we construct a multicast protocol like this, you basically have each node joining a group by sending a message to a rendezvous point. Note that for different groups this could be different. If you have hash of soldiers, it could be here. So then it's not like a point of failure problem. Each group's hash can go to a different location. So basically what's going to happen is each node is going to update its location to the rendezvous point. And finally, when a source wants to deliver a packet to this multicast group of medics, he just asks the rendezvous point for the locations of the group, constructs a tree and delivers the packets. Okay? So this is a problem because it's not scalable with group size. So there are two problems here. There's a problem in group and location management. For example, you have increased update traffic at the RP as the number of people increase. So if you have 20 group members versus 50, the number of packets sent to the RP in the previous slide are going to increase. Also, all these 50 group members and their locations have to be stored at the RP. And that's a problem because the RP is going to do a handoff. So the more the state, the harder the handoff. And also the sources have to retrieve all these groups and their locations from the RP. So that also becomes a problem with this increasing group size. There's another important problem. When you want to deliver data, you have to encode the tree in the packet. So if the group size is large, you have to encode 40 locations in a packet, which is too large compared to the payload of the packet itself. So as you can see, MGH is not directly usable for implementing a scalable multicast service. But interestingly, we can use the well-known hierarchy concept. You can break down a group into manageable size subgroups using a hierarchy. And MGH can actually be used to implement this virtual hierarchy. So although MGH cannot be used in the plain sense, it can still be leveraged to implement a hierarchy, which is then scalable with mobility. So let's see how that's done. So you have this area here. Earlier everybody was sending it to the RP. So instead, let's divide the area into D squared cells, where D is a decomposition index. And you can also have a hierarchy level, so you can recursively partition each of these D squared cells into further cells. If we do this, all each node does is, instead of sending messages to the RP, you first join the network to the RP, you find the networks D and H, then when you hash medics, you actually hash in the smaller area. So this hash actually goes to an access AP. Okay, so again note that this AP is a virtual location, it's not a real node. It's again a hash, but it's in a smaller square. So the idea is this AP is now going to manage a smaller subgroup of nodes. So that handoff, etc. is not a problem. And all the AP does is just tell the RP whether there are some members in its cell. So it's just a binary message saying there is a member and there is no member. That's all. So this hash function is the same as the original MGH hash function, except that it's scoped to be within this area. So now how things will work is, all the members, when they're moving, they can send updates of their location to the AP. The AP will just tell the RP that there are members in my cell. Okay, so he knows this. Now okay, let me go to the next slide, it'll be better. Sorry. So all these nodes are updating their locations to the access point, and the access point is just telling the rendezvous point that there is a member in my cell. So now when this source wants to send a multicast to all these people, he just sends a packet to the RP asking for which cells have members. And this is just d square bits of information. This is got back by the source. The source then constructs a tree to these APs. And this requires no encoding because he just computes the hash functions. He knows already where these APs are. He makes a tree which is the source to AP tree. So the multicast packet is sent there using a tree. And then the AP further makes a tree from itself to all these group members. So the idea why this works is because the member to AP updates, these members to this AP updates, contain the location information, but there are only few members because we have broken down the area into subgroups. Secondly, the AP to RP updates are sent only when membership changes in a cell. So they are much less frequent. It's like a 1-bit flag. And also the update update traffic and state of the RP is reduced. So we've solved the problem that the state and update traffic of the RP is increasing with group size. So let's see how we solve the encoding overhead. So as I told you before, data delivery is affected by increasing encoding overheads as group size increases. If you use two trees like this, the source of the AP tree, the encoding overhead is limited to d square bits, and no location information needs to be encoded because each person can just compute the hash function. From the AP to member trees, they are limited membership because you've broken down the subgroups, so the encoding overhead is also low. So for example, in one AP, it will probably be three clients. We just have to put 3 locations in the packet.
Can you explain why there's no location information? First part,
right. Right. So for example, if this source is told which of these people have members, so you can just say, okay, 1000000001, like that. So you have just a bit. So then he knows which cell is where. So he knows this cell means here. He can compute this hash function here and find out which location this is himself, because he knows it's just a matter of computing a hash function, right, to find the location of this AP. So each node can just compute the hash function. You don't have to encode the locations in it. So as long as you tell him which are the cells that have members, that's all you need to know. So any node, so for example, when it gets here, this AP also knows how to compute this hash function. So you can simply do it like that.
So what do you hash from? You hash what into the API?
So you hash your medics only. You hash medics.
Hash medics.
And also you give him the D. So based on the D and your current location, you know where to hash. So for example, if you are here, you will hash here. If you are here, you will hash here. If you are here, you will hash here. That way. But it's still medics.
Okay.
Whereas if you hash in the bigger area, you would hash here, something like that. So it's a hash in a smaller area. That's all it is really. It's the same code basically. So basically we have these two trees which don't have encoding overhead. As a side note, I also talk about how HRPM construct trees. So HRPM is the protocol we are building. So one way is to use the location of all the nodes, members and non-members. So this is high overhead because this is like a standard tree problem. If you have all the nodes, how do you make a multicast tree to the group members? The problem with this is everybody has to update the locations, and through simulation we found that there is no significant benefit of this approach. You don't get that much of an gain in terms of the efficiency of the protocol. So what we do is simply use the location of only group members. So only group members are going to update their locations, and so a source knows the group members and he can build this unicast tree. So suppose this is a source and he's building a tree like this. He's just going to say the tree, he should go here, here and here, and between these points he uses geographic routing because he knows the locations. Right? So it's not that, so it's like an overlay tree sort of. So an important thing here is how do you choose this D and H? So I talked about this D and this H. So it sounds very complex. So how do you choose it? So the choice of D and H is an important design choice, and it's chosen per group. So for example, the medics group, if it has 10 members, he doesn't need to do hierarchy. Whereas the soldiers group has 200 members, he may need to do a hierarchy. So every group decides on this D and H based on the group size. So the RP decides this. The values of D and H depend on how much overhead you are willing to pay. So we had some constraints and we found expressions to get this value of D and H. So the main conclusion is that a 2-level hierarchy is enough. So what I showed you here, so this kind of hierarchy is enough. So you don't need to further partition this into more cells. And the reason is that, again, if you apply the same principle that we are working with practical network sizes, if the overhead of encoding the locations is limited to 20% of payload, we can support up to 550-800 group members, which is pretty large for most applications. So basically we are just going to use one level hierarchy. That's you have one area and it's divided into cells. So now it remains to show that HRPM is scalable to current multicast protocols, and how it works, how it scales with group size, network size, number of groups, and number of sources. The 4 parameters. So again, we implemented in GLOMOSIM, and we use a similar model as the earlier paper, and we compare it to ODMRP. So ODMRP is the mesh-based protocol which was proposed in '99. The metrics we use for comparison are MDR. So when you send a packet, how many receivers are able to achieve the? So if the group size is 20 and your multicast packet reaches 20, then your MDR is 1. So it depends on how many people are able to receive your packets. Then we have this encoding overhead. How much overhead is there in encoding the locations and group members, and we also have control overhead and delay. So the first thing we see is that on the x-axis we have D. So we want to show that the HRPM hierarchy reduces the encoding overhead. So when D is 1, it's the original RPM, which is you just hash to the RP and RP does everything. There is no hierarchy at all. So when you have this, you can see that the overhead of encoding the location grows to 40% as the group size is increased from 25 to 250. And in fact, for larger group sizes, 150 and 250, a D equal to 1 cannot work because the packet is so large that the MAC layer cannot even transmit it, because there's so much of encoding overhead. So you have to encode 150 groups members and their locations. So for D equal to 1, nothing is not going to work. As we increase D to 4, so when D is 4, that means you have 16 cells, like the example I was showing you. So as you increase D equal to D to 4, you can see that the encoding overhead comes down to 15%. And the good thing is that this is achieved without any increase in control overhead. So this is the power of MGH again. So because of MGH, you can do all these hierarchy constructions and all that stuff without having to do any kind of flooding or deciding who's the leader here, who's the leader there. So as you can see, as D increases, the control overhead of the protocol remains basically flat. Sorry. Next thing we need to show is that HRPM scales with group size. So we took one multicast group, say a medics group, and we increased the number of group members from 0 to 250. So as you can see, the overhead of HRPM compared to ODMRP is lower. And we can also see that the encoding overhead, so if you didn't have a hierarchy, the encoding overhead would grow like this, and after this you cannot even support the group members. Whereas the encoding overhead is maintained at the constant level by HRPM. The reason is that as the group size increases, you can adjust the D and H to this group size and maintain the encoding overhead below 10%.
If the group is growing, is that a problem? So the rendezvous point decides what D and H is doing. Correct. So what if the group starts small and then?
Yeah. So as it's growing, he can adjust the D. So he'll send a multicast to all the current group members, saying that the D has changed. So they'll change the hash function. That's very important. So here that's exactly what's happening. So as the group is growing, the RP needs to do this adjustment. Otherwise, it's not going to have this performance. That's very important. So the next thing we show is that the delivery ratios are comparable to ODMRP. So it delivers close to 100% of packets in such a large network. So the one problem that HRPM has is delay. So the average delay of packet delivery is higher, but still useful for many applications. For example, the average delay, this is in seconds. So the average delay is around 50 milliseconds for a large group size. But the main reason for this is we are using unicast. So it's almost like reliable multicast. Whereas ODMRP just floods the network, so it doesn't even know how many packets are going to get through. So we have to pay a price for the reliability, and so the delay is slightly higher. But we'll show that this is acceptable given that it's below the threshold for many applications, as well as that you don't really care about it if you want to do a high throughput download or something like that. So what happens when we increase the number of sources? So we had one group and we increase the number of group members. So what if we keep the group constant, the group size constant, and change the number of sources of the group? So what happens is ODMRP overhead increases by 400% as the number of sources increases from 1 to 5. Because each source needs to build its own tree. So you can imagine one source is there, one source is here. His delivery mesh is going to be different from his delivery mesh. So they each need to flood the network to make their delivery structure. However, HRPM overhead remains almost the same because all multiple sources need to do is contact the RP, get a list of people, and just make their own tree. So as the number of sources increase, HRPM is much more scalable. And this was observed for both small and large group sizes. Now if you look at the increasing number of groups, so here what we're doing is, instead of one group, we have 45 groups. So there, and we keep the number of receivers constant. So for example, you can have 18 into 2 versus 12 into 3. So you have 12 groups of size 3 or 18 groups of size 2. So we keep the number of receivers constant at 180 and adjust the number of groups like this. So look at what happens to ODMRP. So as the number of groups increase from 500 to 40, from 5 to 45, the overhead grows from 100,000 to 2 million. So it's really very bad. And the reason for this is, again, each group needs to do its own tree delivery, mesh construction and maintenance with mobility. But the overhead is very high. And if you look at the delivery ratio, it delivers only for 60% of the packets. So 40% of packets are lost because of mobility. The nodes have gone all over the place. And also this high overhead is taking away all the capacity of the network. So these packets are lost. So HRPM scales well with increasing number of groups. So now we have satisfied 3 of the requirements. The last thing is the network size. So again, as the network size increases, topology-based protocols like ODMRP again do flooding. So the overhead increases and they're not able to maintain the structure. So again, if you look at the delivery ratios, HRPM can deliver up to 30% more packets than ODMRP for both group of size 5 and group of size 30. So HRPM is able to leverage this nice virtual hierarchy to be able to sort of be scalable across all these parameters. So the summary of the results are that HRPM improves the scalability of multicast. We get more than 95% delivery ratio up to 250 group members in a 500 node network. Same as the number of groups increases from 2 to 45. And also as the network scales up to 1,000 nodes with up to 300 group members. So the key thing here is that we are able to use MGH to enable a lightweight virtual hierarchy that reduces the encoding overhead and allows multicast to be robust to mobility. So the fact is that we need a hierarchy because the groups are so large. But if the hierarchy imposes overhead, then it's no use, just like GLS. So you don't want complexity. So MGH gives us a hierarchy without the complexity. So that's why it's scalable and robust with mobility. So in conclusion, mobile geographic hashing, we feel, is a powerful abstraction that can help construct scalable protocols in dynamic networks where nodes move around continuously. MGH basically decouples the data location and data storage. So as you can see, he just locates the data at XY, but stores it in whichever node is closest to XY. So you basically handle mobility using virtually stationary location servers. So in both HRPM and GHLS, we have these RPs and APs, but these are not nodes. You don't have to find this node again. It's just a virtual node. It's a virtually stationary location server, and that's why it's very good with mobility. That's the key point. And we are able to demonstrate the effectiveness of MGH to the scalability improvements in unicast and multicast routing protocols. So using MGH, we are able to scale the current state of the art in both unicast and multicast routing protocols for dynamic networks. And we feel that this is the best way to sort of construct these protocols. So there can be many other uses of MGH for example, data storage, etc. You can even use it for storing data and retrieving it later. We are using it as a location service. So the key point is the virtual stationarity helps in a mobile network because you don't want to track nodes locations. So I'd like to thank you for your time. And I also need 2 slides. I'll be talking about my work on mesh networks after the questions on this. Thank you.